Hi, Assalamualaikum everyone. This video for our group project MAT222. Without wasting time, let's begin.
Okay, before we learn how to use a forward and backward method, firstly we need to know what is forward and backward method. Forward and backward method is a logical reasoning using a forward and backward thinking. And then we need to connect a given information that we get from the question to get the conclusion. For example, let's assume A is hypothesis and B is conclusion. To prove if A then B is true, we need to assume that A is true, and then just this to show that B is true also true. And then why we need to use a forward backward method? Firstly, to connect the assumption with the conclusion. Basically, a question will give us a assumption and the required conclusion, and then we need to thinking using a logical connection to get from the assumption until the conclusion. Next, to ensure every step in the proof is valid. For the method, we cannot skip any step. Just to get the conclusion, we need to forward and backward check. We need to check all of our assumption before we get the logically valid proof. And then, to avoid logical error in a reasoning, we can add our own assumption. We just need to use assumption that question give. And then we need to use a proper justification to get the conclusion.
Forward process means we start with the given information or assumption in the question. From there, we apply logical reasoning step by step until we reach the conclusion. This method is also known as a direct proof because we move directly from what is given to what we want to prove without making any opposite assumptions. The forward process is suitable when the information is clear, the conclusion is straightforward, and the statement usually involves if-then statement. It is commonly used when a simple and direct proof is possible, especially in basic algebra or number theory problems. Now, let's look at the steps of the forward process using an example. The statement we want to prove is, if n is even, then n squared is even. Step 1, we start by assuming the given condition, so we assume that n is even. Step 2, we apply logical or algebraic steps. We square n, so n squared becomes 2k to the power of 2, which is 4k squared. Step 4, we reach the conclusion. Because 4k squared is even, we can conclude that n squared is even. This shows how the forward process works by moving logically from the assumption to the conclusion.
Now we are looking at the backward process. Instead of starting with what we know, we begin with what we want to prove. The idea is to work logically backward until we reach the original premise. This method is especially useful when the conclusion is clear and we understand the logical implications involved. By retracing the steps from the conclusion to the assumptions, we can clearly justify why a statement must be true. The backward process works best in a specific situation. First, the conclusion must be clear and well defined. Second, we need to know the logical or algebraic relationships involved. And finally, this method helps us identify the initial assumptions required for the conclusion to hold. When these conditions are met, working backwards often makes proofs simpler and more structured. Now, let's apply the backward process using a simple example. We want to prove if x squared is divisible by 3, then x is divisible by 3. We will begin with the conclusion and work backward to the given condition. We begin by assuming the conclusion that x is divisible by 3. This gives us a starting point for working backward. If x is divisible by 3, then x can be written as 3k for some integer k. This rewrites the conclusion in a usable mathematical form. Substituting x equals 3k, we get x squared equals 9k squared. Since this expression is divisible by 3, x squared must be divisible by 3. We have now reached the original condition because our backward steps lead directly to it. The conclusion follows logically. This completes the proof.
I will explain about the question 1. We are given the proposition, which is if n is a positive odd integer, then n open bracket n plus 2 close bracket is an odd positive integer. So we have to get our A and B first, which is A stand for hypothesis, B stand for conclusion. Then we have to get our A1 next, which is n equal to 2k plus 1 for some integer k, because it's already set in A, where n is a positive odd integer. Then we have to get our B1 next, which is n open bracket n plus 2 close bracket is an odd positive integer. So we can write as n open bracket n plus 2 close bracket equal to 2m plus 1 for some integer m. Then after you guys expanding, simplifying, factorizing, and you guys have to rewrite this final expression as in A4, which is 2 open bracket 2k square plus 4k plus 1 close bracket plus 1. Then you guys can using logical connective, which is take the final expression to equal to 2m plus 1, which is our conclusion. Then you guys can see that m is equal to 2k square plus 4k plus 1.
I'm going to explain question 2, and it says, by using the forward backward method, prove the proposition. If p and q are consecutive integers and p is even, then p squared minus q squared plus 5 is divisible by 4. From the question, we can get A. P and q are consecutive integers and p is even. Also B. P squared minus q squared plus 5 is divisible by 4. From that, you can get P1, which shows that p squared minus q squared plus 5 is equal to 4k, with k being an element. This is because it is divisible by 4. Now for A1, p is equal to 2t because it uses the formula for even integers, and p and q is equal to 2t plus 1, which uses the formula for odd. This is because p and q are consecutive integers, so that means if p is even, then q must be the opposite, which is odd. Now for A2, we have to replace p and q of p1 for the formulas in A1, then factorize it, and it will give us 4 minus 4t. After that, we have to change the shape of the answer by taking out 4 to get the value of k, as you can see in A3, which shows that p squared minus q squared plus 5 is equal to 4k, where k is equal to minus t1. Therefore, A3 is logically equivalent to B1. Thank you.